This is my lab report for Lab 4, Oscillations. The objectives of this lab were to examine the motion of the swinging spring system, model that motion using VIDLE for Python, and discuss how Newton's second law helps us create and understand that model. So this is what I got when I used Tracker to analyze the motion of the system. There are only two forces acting on the system, the force of gravity and the spring force. Notice how the orientation of the seemingly elliptical motion changes during the motion. This is due to the different periods of motion in the x and y directions. When you graph the data of x position versus time and y position versus time, you get a graph that looks like this. The x values fluctuate around 0, which is the x value when the system is at rest. The y values move around about -0.7, which is the relaxed length of the spring at rest. This is where you can clearly see the difference in periods of the x and y components. Newton's second law is what will help make the model. dp dt equals mass times dv dt, where dp dt equals the sum of all individual forces acting on the system. Like we already said, there are only two forces acting on the mass, the force of gravity and the spring force. These are the initial conditions. The object's mass, initial velocity, and initial position are all shown. I use the given values for the spring constant and relaxed length as well. The next step is to plug in those values to the Python code. This is what the initial conditions section of my Lab 4 code looks like. Next, I define K to be kinetic energy, UG to be the gravitational potential energy, and US to be the spring's potential energy. Within the while loop, the meat of the code is adding up the forces of gravity and spring and using an iterative form of Newton's second law to update velocity and position to create a graph that looks like this. Just from observation, my model seems to be a good fit. The orientation of the seemingly elliptical motion changes direction just like from the observed motion. The data from the model looks like this when plotted. Just like the observed data, the x values fluctuate around 0 and the y values go around about -0.7. That is a good sign that the model is a good fit for the observed motion. When the two graphs are laid one on top of the other, there's a clear correlation between them. The x direction data is nearly perfect in line, and the y direction data seems only to be off by a translation of a fraction of a second, that's all. Now for the what does it mean questions. Number 1. For your model system, is the energy principle satisfied? Number 2. Compare the two periods for the x and y motion. First off, is the energy principle satisfied? So this looks like a lot of lines, but it is a graph of all of the changes in energy of the system. Blue is the change in kinetic energy, red is the change in spring potential energy, and green is the change in gravitational potential energy. Now, in a perfect world, they would all add up to 0, and the yellow line, which is the change in total energy, would be 0. However, for my data, it did not. There is a small change in total energy over time. But before everyone freaks out and claims, I broke the energy principle, consider the magnitude of the change. The total change is about 10 to the -4. Based on this, I would conclude that the energy principle is satisfied and the changes are due to human error. Next is to compare the two periods for the x and y motion. For the x direction, the period is 1.6524 seconds, and for the y direction, the period is 1.5004 seconds. The change is due to the fact that there is also a pendulum period at play here. Since there is motion in the x direction, the spring acts as both a spring and a pendulum, with a constantly changing length. This accounts for the complicated motion and the difference in periods. This concludes my lab report for Oscillations.